Hello folks, how's it going? Welcome to another one of my videos. I don't know why I paused there, but I did. Anyhow, we're gonna keep that in. Yes, the title is actually not a clickbait. This is a Titan Z or Titan Z, depending on how you want to pronounce it. It was quite an expensive card when it launched, $3,000. It's essentially two Titan Black, GTX Titan Blacks in a single graphic card. So you have 2,880 shaders per core, 384-bit memory bus per core, and 6 GB of 7 GHz GDDR5 per core. Yeah, $3,000. That's, well, when Titan Black launched, that was $1,000. So put two of those together and add another on top, that would be the price of this. So this had the title of the fastest graphic card in the world for a few days or weeks or months till R9 295X2 came along. Then they traded blows for a while, even though the 295X2 was half the price and was better cooled because it had an AIO or all-in-one cooler. Anyways, what we're gonna do to this legendary piece of kit, which is actually in quite a good condition, is take it apart, clean it, restore it to factory condition, and even improve it a bit for what I like to call a RESTOMOD. Well, we're gonna change the thermal paste to something a lot more potent, because out of the box stock, this card runs quite hot. We're talking getting close to 90 degrees with the power temperature sliders maxed out. So we're going to see if we can improve that. After that, we're going to mod the BIOS, add a little bit more voltage, a lot more wattage headroom, or TDP, and bake in some really high clocks as far as we can go. Yeah, we're not going to push this card like beyond its limits. It's going to be alright. We're not going to kill it, but we're going to make it run a lot better than when it left the factory. Stay tuned for more. Okay, so there are quite a few ways to skin a cat, as I'm sure you all know. Now, to take this apart, it depends what you want to access. So if we flip this card around, there are 4 main screws, and 1, 2, 3, 4, 5, 6, maybe somewhere around here, about 6 secondary screws that keeps the back plate attached to the other side of the card. There's also another plate running on the front of the card. So we're not going to do that because doing all of this will tear all the thermal pads for the VRMs and memory, and although we could replace them, there's really no need because this card, like I said, is already in a really good condition, haven't been used much, and we're not going to need that. Instead, we're just going to concentrate on improving cooling for the core, which, as you can see, I already took 4 of these screws out to undo one of the 2 main heat sinks. But before that, I had to figure out how to disassemble the card in the most efficient way, instead of, undoing a whole bunch of screws and doing stuff that it's not really necessary. So all I had to do is take out 4 screws to take the main shroud off. So let's take a look at that. These 2 screws at the back, one here and another one here. Those 2, the one here. And if we flip the car over, another one here. 4 screws, take those out, and you can take the main shroud off. So with a little bit of wiggle, it comes off. Don't break it, don't break it, don't break it. So it would probably help if I undo 2 of these side screws that hold the cover in place, but we should be okay. We should be just okay. Yeah, so these 2 side screws I'm talking about. This and that kind of holds the side of the shroud in place, so it makes it a little bit tougher. So we're gonna take those out. Well, actually just loosen one of them. I figured that's the best way to do it. So we'll just loosen this a little bit, and this also a little bit. This is a lot tighter because I haven't done that yet. Yeah, and the shroud just comes off. Ta-da! All done. By the way, those 2 screws on the side, we're using a 2mm hexagonal screwdriver. For the 4 initial screws that I said to take out, you need 1.5 millimeter hexagonal screwdriver. Those are quite common. I don't suspect many people will do this anyway, so it's all right. So there's the shroud, 2 plexiglasses, the center hub for fans. You got a bunch of screws here that you do not need to take out. I see just 12 on the front. I think these are the one that, yeah, 4 of these holds the plexiglass in place. Nice cover. Black heat sinks. These are quite nice. I already loosened one of these. Oh, by the way, here's the GeForce logo. Well, it's there. That's all I'll say about it. And it kind of gets embedded into this cutout here. Kind of difficult to put it back on because there's no solid way to keep it in place. But anyways, so I already took this heatsink off. Kind of gotta wiggle it a little bit because the 2 right side standoffs for the screws, those are underneath this secondary central heat sinks for the VRMs and the fan. So you could take this plate off by loosening those screws, or we could just wiggle this a little bit and this comes off. So as you can see, well, this is a vapor chamber design, as it's kind of the only way to do this kind of small form factor graphic cards without sacrificing the thermals too much. There's your GK110 core, the Titan Black core. I've already cleaned it a little bit. The thermal paste is gone, but we're gonna do the other one. So let's do it together. Hopefully I'm not taking too long. As you can see, we got a void warranty sticker, which, by the way, if you're in the States, these are not enforceable anymore. These are just to, if you see them, you can ignore them. The manufacturers don't have any way of enforcing that. I'm in Canada, it doesn't matter. This card is, what, 5-6 years old at this point? There's no warranty left on this. So we're gonna be alright. Let's just screw through this. At least we know because that thing is in place, that we got an unmolested graphic card. So that's a good thing. If you don't know what you're doing, learn what you're gonna do first, then do it. If you've never taken apart a graphic card, it's not a good idea to start doing it on a $3,000, formerly $3,000 graphic card. But I've taken apart hundreds of graphic cards in my time, so this will be alright. I hope so. Now, is the 4th one loose enough? Yeah, it's loose enough. So this is also stuck under the central heatsink a little bit, so we're gonna wiggle it. Actually, this might be still in place. You might have to remove the sticker, which isn't part of the graphic card anyway. Like these cards, they're not aftermarket. All of these were made exclusively by Nvidia, sold to partners, and then they sold them to customers. So they're not, these are completely reference designs. They're alright, they got 5-phase power designs and so forth. They can get the job done. Too expensive though, $3,000, kill me. Oh, by the way, when in Canada, yeah, you pay a lot of tax and the conversion rate. So this actually, when it launched, this was closer to $4,000 for us Canucks here. Let's see if we can wiggle this free. Don't want to put too much pressure. You don't want to damage the PCB. Is this? Oh, I don't think we can take this off. No. See, the hole is here, and the clearance ends here, so we have to take the central heatsink off for the VRMs. I don't think we're gonna wiggle our way out of this. No sir. Alright, let's do that. First time for everything. So we're looking at 6 screws. 1, 2, 3, 4, 5, 6. Let's try to wiggle this free. Okay guys, something should be quite evident by now. The video and audio has changed. Yes, my Canon E60 DSLR decided to die in the middle of recording. So yeah, it's down to my crappy iPhone to finish this video. You only needed to remove one screw from the back to disassemble everything. So essentially, this center screw here, that's the one you had to take out to remove the whole central heatsink. That comes out. You could see the thermal pads. Yes, so there's the VRM, 5-phase for each GPU. I don't know the exact detail of it, but it's adequate. Also the PLX chip here. And now, the final heatsink comes off. Ta-da! Yeah, so let's clean it and see what we can do. Right. Now, what we're gonna do for the thermal paste is liquid metal. Hold on. Yes. Liquid metal, yes. Specifically what I have right now is Cool Laboratory. I have to get up to see the camera. Cool Laboratory Liquid Ultra. Yeah, so liquid metal, funny thing, it's conductive. That's not good around electronics, is it? Being electrically conductive. Well, we can do something about that. Solver solution is a sexy nail polish. Yes. No, I don't use this on myself. This is just preserved for graphic cards and electronics. So see these small little SMDs and capacitors? Yeah, if you get thermal paste on those, it's not a guarantee that it'll kill the card, but it'll interfere with operation. Maybe get a black screen. Maybe your whole VRM blew up, or your core blows up, and that's a $3,000 graphic card down the drain. So let's not do that. So nail polish, or to use a special one. Is this the correct orientation, or is it this way? Well, I can see it this way, but the camera's backwards. Anyway, it's liquid tape, same as nail polish, really. Liquid electrical tape. You can use whatever you want. Nail polish is more readily available. So we're just gonna clean the area around the GPU with some of these applicators or ear cleaners and some isopropyl alcohol. 99% isopropyl alcohol. Just to make better contact, really. You don't really have to do this part, but you have the material, why not use them? Let it dry for a second. So you just want to touch these SMDs. Nail polish is, well, non-conductive electrically. And you can use any color you want. I think that's the draw for this kind of thing. You can color your 2880 shader count GPU SMDs any color you want. We're just using clear nail polish for this application. Now for other health related and beauty videos, please check out, no, I don't do that. Please stop. Should have stopped a long time ago. Okay. Yeah, we also cleaned the surface of the GPU with some isopropyl alcohol or rubbing alcohol, same thing really. And heatsink as well. Yeah, that's good enough to just clean all the residue and anything that might be left on it and just give it a good polish. Okay, so the surface has been cleaned properly this time, and I also applied nail polish to, no, not my fingers, the second GPU. Now, let's do some liquid metal. Some has oozed off on the side. Anyway, for that, we're just going to use a Q-tip again. Let's get some of that off. How did that get up there? and you basically just want to spread it around. Yeah, it's very exciting. It's like watching paint dry. Yeah, we're just going to do one GPU, by the way, because once you've seen one, you've seen it all. Apply some of that liquid metal on the heatsink as well to break the surface tension, like I said. That should do it. Okay folks, this is the end of the video. Well, it's going to be soon, and pat yourself on the back for making it so far. Sorry about the humming noise in the background. I have a fan running. It's quite hot today. It's been several days since the tests have been done, and just been procrastinating for some reason or another. Anyway, here we are. This is the stock run from the GPU. This is completely stock GPU running 10 minutes of Unigine Valley on my test bench. The primary temperatures for the primary core, 89 degrees and 82 degrees for the secondary core. The voltages don't tell the whole story. 1150 millivolt and 1125 millivolt for the secondary. They drop quite a bit under load after 10 minutes. The card gets quite hot. It starts to throttle a little bit. It's normal. The power target, as you can see, 120%. That's essentially what the stock BIOS allows you to do, to max it out to 120. Power consumption, we can see these are for the cores only. It's a rough estimate. I wouldn't consider it it's not the whole power consumption of the card. It's essentially just the core. So 230 maximum, 215 maximum for the secondary. Yeah, they still drop a bit after, you know, the 10-minute burn-in period. Here you can see the stock BIOS. The boost clocks are advertised at 876 megahertz. The average I found out when the card was completely heat soaked was about 1000 megahertz, about 1000 to 1010 megahertz. Sometimes a little bit less, sometimes a little bit more, depending on how heavy the scene was. And it's quite a lot higher than the advertised boost speed, over 100 megahertz. So I guess kudos to Nvidia for using conservative estimates. You know, you install this card, you expect these, you get a lot more than that. Anyway, so this the top part is after I applied the new thermal paste, the liquid metal, and the results are interesting, although they don't tell the whole story. Again, this is still with the stock BIOS, I might add. So as you can see, temperatures 87, 81. It's like, hey, that's not a whole lot better. Well, it kind of is, given that 2 degrees and 1 degrees, although not substantial, if we look at the fan speed, 2800 versus almost 3100 RPM. So we're running the fan 200. The fan is set on auto, by the way. So 250 RPM lower and still getting better temperatures. So that's quite a win. The card is now running much more efficiently, more thermally efficiently. The sustained clocks were around the same, little bit more, but as you can see, because we have a little bit more thermal headroom, the power consumption went up a little bit higher. So 5 watts on the primary core, another 10 watts on the secondary core. The voltages were allowed to go a little bit higher too. This is still the same stock BIOS. So the improvement was decent. Not as much as I was hoping for, but given that the RPM is 250 lower, the card runs cooler and quieter. So it's a win-win. Now we look at my modified BIOS. This is an overview. So essentially, these clocks are, I baked these clocks with modified voltages and power targets. This is the best I could do with this card. A little bit, again, conservative. Like the memory is running at 1950, which is GDDR5. It's the stock is 7 gigahertz at 1750. That's 7 gigahertz effective. This is 7.8 gigahertz. So it's quite a bit higher. The clocks are now locked at essentially 1100 megahertz or 1098. And I did that through BIOS modification using Kepler BIOS Editor. Quite a interesting, nice tool. So what I did was, this 1087 millivolt and 1062 millivolt. That's essentially what the card hit after 5 to 10 minutes after it's been under load. So those are the sustained voltages. I reduced those a little bit. So in the modified BIOS, I turned that to 1075 millivolt and 1050 millivolt stable throughout the whole load. So the card doesn't start at 1150. It starts at 1075 and stays 1075 millivolt throughout the whole benchmark or 3D application you're going to run. So it's completely locked down. There is no variation in clocks. It runs at 1098 from start to finish. I didn't take a screenshot like this. I didn't test the 10-minute burnout period, but the temps were lower, around 85 degrees to 80 degrees. As you could imagine, having lower temps, the RPM was even lower. So I improved the temperatures, the power consumption, and the clocks and the stability of the clocks. So all around, this is better than it could have possibly ever been before it left the factory floor. So I'm kind of happy with that. 1100 megahertz could have gone a little bit higher. Maybe I could have pushed it to 1125, but given that 25 megahertz risking stability for a card that I would consider a daily gaming card, 25 megahertz won't make a whole difference. So I'll always side with stability. So pixel rate, texture, fill rate went up accordingly. Although this again doesn't tell the whole story, because these numbers should be around 1000 megahertz. So we essentially gained 100 megahertz on the core and about 800 megahertz on the memory. Good gains overall. Better fan speed, like I said, better temperatures, better everything. Then I decided to run a Unigine Valley benchmark at 1440p. At 1080p, the difference isn't as prominent as I would like it to see, mainly because my test bench uses a 3770K at 4.7 gigahertz, kind of aging at this point. So there's a little bit of a bottleneck at 1080p. But at 1440p, you can see the difference. So FPS 70.5 FPS completely stock, and with my mod is at 76.4. Doesn't seem like a whole lot, but again, it's a $3,000 graphic card that we improved in every single way. And if we take the average, so we'll just take the score, 3195 divided by 2951, 8.3% faster. Again, with better thermals, lower noise, it's a success. So the question you might be asking yourself is, hey, if you can do all of this, make the card run cooler, quieter, higher performance, more efficient, why won't Nvidia do this with their cards? Well, the thing is, there are a lot of variables involved with these cards. As expensive as it is, Nvidia still makes tens of thousands, maybe hundreds of thousands of these cards, and they can't just sit someone down and test all of these cards individually, because this fine-tuning took about several hours, maybe a good day for me to do. And although I can do it because I have access to a single card, there's no way to do this sort of thing on a mass scale. And there's a lot of variability, like what's the ASIC quality of the chip, what's the tolerances on it. They have different voltage sweet spots. Anything has to be tuned individually on a and a case-by-case basis. So yeah, you can understand that, but it shows even on a thermally limited high-end graphic card, you can still improve it. And yeah, I hope you guys learned something today. I hope I didn't ramble on too much. And if you'd like to see more of this type of content, going in depth, see all the nitty-gritty stuff that I can do with these graphic cards. If you like more of this sort of content, more hardware reviews, it's not really a review, but like a RESTOMOD sort of thing, do let me know in the comments. I do read them. I do, I promise. Okay, thanks for watching, guys, and I'll see you in the next one.